to get an accurate picture of the greenhouse gases in our atmosphere, we need to measure from the ground to space. The question is, how do you do it? Here at Lauder in Central Otago, they're looking to the sun for answers. The scientist asking the questions is Vanessa Sherlock.
The next generation of greenhouse gas measurement techniques give you a measurement of the greenhouse gas abundances through the entire depth of the atmosphere.
This is called total column measurement and is much more accurate than previous methods. But why is more accuracy important?
As time goes on, it's increasingly likely that we're going to want to know that nations are in fact reducing emissions in accordance to protocols like Kyoto, and politicians need to know that the measures that they're taking to mitigate greenhouse gas emissions are being effective, and they also need to know that everybody is doing what they signed up to do. We have a very simple telescope which points at the centre of the sun, and we record that sunlight.
From this sunlight, Vanessa can extract some incredible information, the exact concentration of every individual greenhouse gas.
To me, this is part of the magic of the whole thing. Each of these greenhouse gases actually has a kind of unique fingerprint.
This means that every different type of molecule absorbs light in a distinctive way. So Vanessa analyses the light that reaches the Earth's surface by splitting it into its full spectrum. Then she tries to find out what tiny bits of the spectrum are missing.
Okay, so unfortunately it's cloudy today, but usually we'd have the sun coming down from the solar tracker on the roof and being piped into the instrument using this mirror here. And then we focus the beams onto this beam splitter.
This is where the light is split into all of the frequencies of the spectrum and is then sent to a computer for analysis. Achieving a sustainable society may be the biggest challenge of an entire generation, and the generation of power is the biggest part of that challenge. It seems that our love affair with oil is ending in tears. Many suggest that we are nearing the peak of global oil production, and from there it will be a short and painful trip down. We have already made good use of natural energy sources, and almost 3/4 of our electricity comes from renewable sources, the majority from hydro. But it is this small chunk of new renewables that we are looking to expand to take the place of fossil fuels and meet our rising energy needs. Possibly the application with the greatest potential is the wonderful world of magnets.
Without magnets, you'd be back in the Stone Age, because most of the systems that we use are powered by electricity, which is generated with some form of magnetism.
This is because magnetism and electricity generation are inextricably linked. A magnet has two poles, north and south. These poles are attracted to each other, so a magnetic field passes between them. Now let's look at a conducting material. It conducts electricity by moving electrons, but when there is no current, the electrons are relatively static. If we bring a magnet towards the conductor, its magnetic field causes the electrons to move, creating a current. Then things get even more interesting. This current creates a magnetic field of its own. Here we've got a sample of the superconductor wire, but it's not in its superconducting state yet. To do that, I've got to cool it to around -200 degrees Celsius, which I'm going to do with liquid nitrogen. The colder the superconductor becomes, the greater the conductivity, and the stronger the magnetic field it can generate. So to test this, we'll add a magnet. And it levitates. So the superconductor has become strongly magnetic and created a force large enough to defy gravity. I could play with this for hours. One petrochemical that desperately needs to be replaced is polystyrene. We use this product in unimaginable quantities, but it takes centuries to break down and is environmentally hazardous. That's definitely what's so special about this helmet.
It's made from polylactic acid.
So this is bio-derived?
Yeah, it's made from corn.
This puffy polystyrene started out life as solid little pellets. It looks like plastic, but you say it's from corn.
Yeah, no, it's the same behaviour and properties as plastic, it's just that it's sustainable and can be renewable.
Corn plastic has been around for a while now, But the problem that Cyan has solved is to find a way to puff these little pellets up so that they can be used as polystyrene. The first step is to use high pressure to force carbon dioxide gas into the solid plastic. That's your CO2 line, is it?
Yeah.
Once this is done, the gas-infused pellets are given a nice warm bath. This softens the plastic and allows the carbon dioxide to escape. Popcorn. Right, Ryan, what am I looking at here?
That is butanol and water mix.
Butanol is a pretty simple chemical, and what's special about this?
That comes directly from a biological organism.
Right, so how have you done that? What do you mean by that?
Well, I've taken a bug, this here. This is Seneca cystis. Now this does photosynthesis, which is what plants do, and it makes sugar from sunlight. And what I've done is basically reprogram it so that it takes that sugar and turns it into a fuel.
So you're getting a direct fuel from this little guy here. How are you doing that?
Bacteria, they're machines, and the cool thing about them is that they're programmable machines. I basically write a program in a piece of DNA, and I've put it into a biological version of a memory stick. And you plug it into that guy, and he installs it onto his genome, and then he runs the program. And that program tells it how to take sugar and turn it into butanol.
So you've essentially made like a biological fuel factory.
Yeah.
As the resources we've come to rely on start to dwindle, we are being forced to look for new ways to replace them. Luckily, nature has been doing this since the beginning of time. Though we have a lot of catching up to do, clever chemists are mimicking these processes and starting to understand some of the wonder that chemistry still has to show us. Without chemistry, we wouldn't have the quality of life that we have today. And without chemistry, we would have no hope of maintaining it.